In the last video, we talked about how to calculate the pH of strong acids or strong bases. Now we need to start dealing with the pH of weak acids. And unfortunately, these are ice method problems, and I don't have a real trick to get around this. Sorry, there isn't like a shortcut. So, let's try an example that doesn't sound like it should be tough at all and see how this plays out. So we want to know, what is the pH of a 1.00 molar acetic acid solution? Okay, we said in previous videos that CH3COOH is a weak acid. It has a Ka value, which we're going to need here. It's equal to 1.8 times 10 to the negative fifth. Okay. The problem is, because this is a weak acid, it's going to dissociate and there's going to be an equilibrium, so we're going to have to do this like an ice method problem, and that's okay. So what we do is we write out the balanced equation of the Ka. So you write out CH3COOH. Ka means it's dissolving in water. It is in equilibrium. Since this is an acid, Ka tells us that it is an acid. This is we're going to get the conjugate base. It's going to lose an H plus, and this will be H3O plus. So our goal is to figure out how much H3O plus there is at equilibrium so that we can take the negative log of it to get the pH. Okay, these are ice method problems. So we need the initial conditions, which is 1.00. We ignore water because it's a liquid, and we're going to assume that we're starting out with none of this. Okay. And what happens is, to get to equilibrium, this is going to decrease by some unknown amount. And because it's all 1 to 1 here, these are both going to increase by one amount, or one equivalent. So for the however much of this drops, this is going to increase by that same amount. So at equilibrium, this is 1.00 minus x, and this is x, and this is x, and we can just ignore water the whole time. Well, for this equation, Ka is products over reactants times concentration of H3O plus divided by the concentration of CH3COOH, and we can ignore the water because it is a liquid. Okay. Well, this is only true at equilibrium, so here's the equilibrium conditions. Ka is 1.8 times 10 to the negative fifth. And these are both x, so I'm just going to write it as x squared, divided by this, which is 1.00 minus x. Okay. The thing I'm about to do is not always true, and I will discuss how to figure it out at the end of this example, but we are going to assume that x is significantly smaller than 1. Okay? So in other words, what we mean by that is 1.00 minus x is essentially equal to 1. Okay? This is not always going to be true, and it's going to get complicated when it's not, but for this problem, we're going to assume it is, and then we'll have to check our assumption at the end. So, if we make this assumption, essentially what we get is 1.8 times 10 to the negative fifth is equal to x squared over 1. Well, that makes life a whole lot easier. You just multiply 1 to the other side, which doesn't even change anything. So x is equal to the square root of 1.8 times 10 to the negative fifth. Okay? And that value is 4.2 times 10 to the negative third. And these are all in terms of molarity. But the reason we're solving for it is x is the concentration of H3O plus at equilibrium. So, to get pH, we take the negative log of the concentration of H3O plus. And the answer, when you type it all in, comes out to 2.4. Okay, so if that's what x is equal to, let's check our assumption. I'm going to switch colors here. So if we take 1.00 minus x, we're hoping that it is equal to 1.00. That was the assumption that we made. We basically got rid of 1.00x and replaced it with 1. So if this is true, then we're fine. Well, if you take 1.00 minus x was 4.2 times 10 to the negative third, you get 0.9958. And since we only get 2 sig figs, that would round up and basically be equal to 1. Okay? So, this actually works out pretty nicely. This is a typical ICE method problem. These come up all the time starting now. But the math doesn't get too bad yet. Okay? What we need to know is whether we can make that assumption or not. There are times when it works and there are times when it doesn't. And doing the entire problem and checking it at the end and then saying, oh, it doesn't work is not the most efficient way to do these problems. So let's learn how to check the assumption from the beginning. Okay, so what we're looking for is that when you subtract x from the concentration, the initial concentration, we're assuming that it's not going to change the concentration very much. So what we need is, for it to be like an order of magnitude bigger. So the easiest way to do it is you can actually check it at the beginning. If the concentration of the acid divided by the concentration of, or divided by Ka is greater than 100, that's 2 orders of magnitude, that means that we can assume that whatever the concentration minus x is equal to the concentration, which is exactly what we did in the last problem. This also works for bases, which we're going to have to deal with eventually. So if you have the concentration of base divided by Kb, if it's also over 100, we can still assume that m minus x equals m. Okay, so honestly, we could check this from the beginning. So on this last problem, we could have just taken the concentration divided by Ka, and as long as it was bigger than 1, we were fine. Okay, so in the previous problem, I guess I'll write that, previous problem. Honestly, 1.00 molar divided by 1.8 times 10 to the negative fifth, all we need is for this to be bigger than 1. If you plug it in your calculator, it comes out to 56,000, which is significantly bigger than 1, which allowed us to basically get rid of this minus x in our equation. Okay. Let's try another example here. Let's try one where the assumption doesn't work. Okay. So just another example. Let's say, what is the pH of a 0.00200 molar CH2Cl COOH solution? So it's essentially acetic acid, but one of the hydrogens has been replaced with a chlorine, which actually makes it a stronger acid. Okay, Ka equals 1.4 times 10 to the negative third. This problem's going to feel just like the last one, but we need to check the assumption first. So I will tell you that you are allowed to make that assumption and make the math easier, but I'm going to need you to prove that it's okay to do so by checking the assumption on the sheet of paper. So that's what we're going to do here. 0.00200 molar divided by 1.4 times 10 to the negative third. You take the concentration divided by Ka. If you plug this in your calculator, you get 1.4, which is not bigger than 100. It's going to make our lives difficult. So smiley, or frowny face, I guess. I don't know. Okay, but otherwise you still set up the problem the same. We just can't make that assumption, which is going to make the math messy at best. So Ka describes this thing losing a proton. You dissolve it in water, equilibrium, you get CH2Cl COO minus plus H3O plus. Okay. We do the ICE method thing. The initial conditions are 0.00200. We can ignore water and we don't have any of those things yet. Again, We only have reactants, so to get to equilibrium, we're going to have to form products. So this is going to decrease by some amount, and these are going to have to increase by the same amount. And for every one of these, we get one of these and one of these. So this comes out to 0.00200 minus x, and this is x, and this is x. Okay? Ka is products over reactants. I'm just going to plug in the value. 1.4 times 10 to the negative third equals products over reactants. Well, the products are both x's, so that's x squared, divided by reactants, which is 0.00200 minus x. We can ignore water because it's a liquid. This, getting rid of this x, would have made life really, really tolerable. Because this x is here, when we multiply everything around, we're going to have to do the quadratic equation. So, a quick review of the quadratic is it's an if-then statement. If you can rearrange the equation to be set up like this, then this weird equation is true. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay? I will point out that if you are solving for a quadratic, there is always a positive answer and a negative answer. We only need the positive answer because we're solving for concentrations. You can't have negative concentrations. So honestly, even though it's written as plus or minus, use the plus one every time. Okay? Now for the hard part. We need to make this equation, we need to take it and rearrange it into that form. So here's where the algebra is going to get a little hairy. Okay, I'm going to rewrite this so we can show all the work here. So 1.4 times 10 to the negative third equals x squared divided by 0.00200 minus x. Well, we want everything equal to 0. So honestly, I need to get this stuff out of the bottom. So I'm going to multiply both sides by 0.00200 minus x. That will make that cancel out, and we'll have to multiply this out on this side. So when you multiply this across here, you're going to take the 0.00200 times this number, which comes out to be 2.8 times 10 to the negative sixth. And then negative x times this is negative 1.4 times 10 to the negative third x. Okay? And this is equal to x squared because we canceled everything else on that side. We want one side of this to be equal to 0, so I'm just going to subtract everything to the other side. So I guess showing my work, I'm going to subtract 2.8 times 10 to the negative sixth off of both sides. Put it all the way over here. Okay, that will cancel that out. And we're going to add, because this is negative, we're going to add 1.4 times 10 to the negative third x to both sides. So that cancels out. And this side is now 0. Okay, this is eating up a lot of space, so I'm going to get a new piece of paper. These problems tend to take a lot of time and space. So if I rewrite this so that it is in this form, we essentially have x squared plus 1.4 times 10 to the negative third x minus 2.8 times 10 to the negative sixth equals 0. So A would be 1, B would be positive 1.4 times 10 to the negative third, and C would be negative 2.8 times 10 to the negative sixth. Okay, I guess I'll label that. A equals 1, that's B, and the negative part is included, but that's C. And then what we do is we plug it into this equation. Okay. So x equals negative b, so negative 1.4 times 10 to the negative third, plus or minus the square root, so I'm just going to do the plus 1, square root of b squared, which is 1.4 times 10 to the negative third. Can't write legibly, sorry. Let's try that again. Negative third. So it's b squared, so we got to square that, minus 4ac. 4a is 1, and c is negative 2.8 times 10 to the negative sixth. All of that over 2a, and a is 1. A is almost always going to be 1. I can't guarantee it always will, but 95% of the time. Okay, So now we need to type all this in a calculator. So, because we're subtracting this off, I'm actually going to do this stuff first. So, 1.4 e to the negative third squared minus, well, actually it's minus times the negative, so I'm actually going to make it plus, because the negatives will cancel out, plus 4 times 2.8 e to the minus 6th. That's the stuff under the square root sign, so now I got to take the square root of that. Okay, minus 1.4 e to the minus third. All of that divided by 2. And I got 0.001138, blah, blah, blah. Okay, sig figs. We basically have 2 sig figs, so it's x is essentially equal to 1.1 times 10 to the minus third molar. And as we said way back at the start of this problem, x is the concentration of H3O+. So, pH is the negative log of this. And the answer is 2.96, which I guess only 2 sig figs. This would be 3.0. Okay. You'll note, essentially, if the assumption works, you don't have to do the quadratic. If it doesn't work, if it comes out to be less than 100, you have to do the quadratic. The quadratic will work every time. I just don't need you to do the quadratic every time. But basically, if it says you're okay to do it, you don't have to do the quadratic. To avoid doing the quadratic, I will need you to prove that it is okay to not use the quadratic. Okay? So, be able to prove the assumption, otherwise plan on doing the quadratic every time. Okay, all right, thank you.